Okay, this is the continuation from exercise 10.3 part 1. This is exercise 10.3 part 2 video. These are some more examples of exercise 10.3 and they are what we did in the lesson on Wednesday the 15th, I think. Okay, exercise 10.3 question 3. Find the value of p for which the quadratic equation x squared plus 2x plus p equals 0 has equal roots. Now, if a quadratic equation has equal roots, then it means it's got two equal roots, or it's really just got one real root. So one real root, it means the same as equal roots. Now, if you've got one real root, then the discriminant equals 0. So discriminant is b squared minus 4ac has to equal 0 in this case. Now, if we look at this equation over here, a is 1, b is 2, and c is p. And b squared is 2 squared minus 4 times 1 times p is 0. So we get that 4 minus 4p equals 0. Taking the 4p to the other side, we get 4 is 4p. Therefore, we can see here that p equals 1. Now, that's enough for this question. You can just stop there. But if you want to really see what this all means, so we can stop here. That's the answer. P is 1. But now we're going to interpret what this result means. So if p is 1, therefore, if I've got real equal roots, it means that my equation is x squared plus 2x plus 1 is 0. Now, if I just look at that, that's actually a perfect square. So x plus 1 squared is 0. And if I sketch that, I know that my solution to this is x is negative 1. It's really x is negative 1 twice. In other words, x is negative 1. So we've got two equal roots, or what we call one root. So, oopsie, I've drawn that wrong. It's actually not over there. My equation, I'll just draw it up here. It's over here. So x equals negative 1 is my root. The y-intercept is 1. The graph actually looks like this. And we can see that this equation only has equal roots, or what we call one real root. When we say equal roots, we mean two equal roots or one real root. That's the first question. Now we're going to look at exercise 10.3, question 5. Okay, this question, find all the values of b for which that equation there, 2x squared plus x plus b plus 1, has real roots. Now, in this equation, a is 2, b is 1, and c is the term without any x's or x squareds. So c is the constant term, which is b plus 1. Now, for real roots, we've got two scenarios. We've either got two real roots or one real root. So, just think, for two real roots, discriminant, I'll just move over here, discriminant is greater than 0. For two equal roots or one real root, we know that discriminant equals 0. Therefore, for all the cases of real roots, we've got discriminant is greater than or equal to 0. Remembering, real roots, discriminant is greater than or equal to 0, is the opposite of not real roots. Not real roots means that the discriminant is less than 0. So, if you want real roots, it's everything apart from not real roots, so the discriminant is greater than or equal to 0. Let's see what the discriminant is. So b squared minus 4ac has to be greater than or equal to 0. So let's see what we've got. b is 1, so 1 squared minus 4 times 2 times c is b plus 1 is greater than or equal to 0. So we've got 1 minus 8 bracket b plus 1 is greater than or equal to 0. 1 minus 8b minus 8 is greater than or equal to 0. In other words, negative 8b minus 7 is greater than or equal to 0, or negative 8b is greater than or equal to positive 7. Now, to make b the subject here, we need to divide by negative 8. And when we divide by negative 8, we need to flip the inequality sign around. So we're really dividing both sides here by negative 8. And we get that b is less than or equal to negative 7 on 8. So if the value of b is less than or equal to negative 7 on 8, then this quadratic equation up here will have real roots. Let's just get an example. Now, that's the end of the question. You stop here, but we're just going to see what this really means. So pick a value of b that's less than negative 7 on 8. Negative 7 on 8, something less than that. If I look at a number line, here's 0, here's -1, -2. Negative 7 on 8 would be here. So a value of b less than -7 on 8 is, for example, b might be -1. Now, if b is -1 and I look at my original equation, for example, if b is -1, my original equation becomes 2x squared plus x plus -1 plus 1. In other words, it becomes 2x squared plus x is 0. If I factorize that out, I get, sorry, I'm just off the screen there. I get x bracket 2x plus 1. So in other words, this is a concave up parabola. Roots are 0 and -1/2. And we can see that if b equals -1, for example, that yes, my equation has real roots. Okay, it's got 2 real roots. I could look at a value, for example, if b was 0, then I should not get real roots. See, I've only got real roots if b is less than or equal to -7 on 8. Let's look at a scenario where b is not less than or equal to -7 on 8. For example, if b equals 0, which is greater than -7 on 8, I'm expecting not real roots. So let's have a look at that. So if b is greater than 0, let's look at my original function. So if b is greater than, sorry, if b equals 0, my original function would be 2x squared plus x plus 0 plus 1. In other words, it would be 2x squared plus x plus 1 is 0. If I try and factorize that, I'm not sure if it's going to work. I don't think it will. Let's just try the discriminant. X is -1 plus or minus the square root of 1 squared minus 4 times 2 times 1. So -1 plus or minus the square root of 1 minus a, over 2 times a, so over 4. -1 plus or minus the square root of -7 on 4. Well, I can see that my discriminant, or the bit under the square root sign, is -7. And so therefore, there are no roots to this equation. I've definitely got no roots here because there's no solution here. So therefore, if b is less than or equal to -7 on 8, I've got roots. And I did an example here. If b was -1, I do have real roots. But if b is greater than -7 on 8, for example, if b is 0, I get that my discriminant is negative, no solution, therefore no real roots. Okay? So that's just giving you an interpretation of the answer as well. We're now going to look at exercise 10.3, question 6. Exercise 10.3, question 6. The question is to find p if this equation, px squared plus 4x plus 2 equals 0, has no real roots. Now, for no real roots, we know that the discriminant is less than 0. So, for no real roots, that means that b squared minus 4ac is less than 0. If we look at this equation, a is p, b is 4, and c is 2. Substituting those in, we get 4 squared, which is 16, minus 4 times p times 2 is less than 0. So 16 minus 8p is less than 0. In other words, -8p is less than -16. Now, we need to divide by -8 to get the p on its own. So we flip the inequality sign around and we get that p is greater than -16 over -8. In other words, that p is greater than 2. So the values of p for which this equation will have no real roots will be anything greater than 2. So for example, so that's my answer, p is greater than 2. Let's just see if this works. For example, let's choose a value of p greater than 2. So for example, if p was greater than 3, p is 3, which happens to be greater than 2, I should have no real roots. Let's have a look. If p is 3, my quadratic equation becomes 3x squared plus 4x plus 2 equals 0. If I work out the discriminant there, if the discriminant's negative, it means I've got no real roots. So let's have a look. Discriminant is b squared minus 4ac, which is 16 minus 4 times 3 times 2. In other words, it's 16 minus 24, which happens to be -8, which is less than 0, therefore no real roots. So we can see that if p is greater than 2, for example, if p is 3, that I have no real roots. If I chose a value of p that was less than 2, I would find that I have roots, okay? So, for example, if p was 1, I would find that I do have roots, okay? But if p is greater than 2, there are no real roots. Okay, let's look at question 7. Exercise 10.3, question 7. Find the values of k for which k plus 2 in brackets x squared plus x plus 3 equals 0 has 2 real unequal roots. Now, if you've got 2 real equal roots, then you've only got 1 root. If you've got 2 real unequal roots, then you've got 2 distinct roots, and therefore, so for 2 real roots, this is like 2 real roots, discriminant's greater than 0. 2 real equal roots is really the same as 1 real root. So for 2 real roots, discriminant's greater than 0. Let's just record what A, B, and C are. A is k plus 2. B is the coefficient of x, which is 1, and C is 3. So for 2 real roots, the discriminant is greater than 0. 2 real unequal roots, discriminant's greater than 0. So substituting in our A, B, C values, we get 1 squared minus 4 times k plus 2 times 3 is greater than 0. You need to multiply this 4 by 3 first, so we get 1 minus 12 bracket k plus 2 is greater than 0. Expanding this, we get 1 minus 12k minus 24 is greater than 0. Or we get minus 12k minus 23 is greater than 0. Solving this, and it's just a linear inequality, we'll just take the 23 over. And now we're dividing by a negative. Oops, I think I may have. So I've got 1 minus 12k minus 24. Yep. So I'm dividing by a negative, and I have to flip my inequality sign around. So therefore k is less than 23 on negative 12, because I'm dividing by negative 12. In other words, k is less than -1 and 11/12. So if I get a value of k that is less than -1 and 11/12, then my equation up here will have 2 real unequal roots. For example, if I chose something like k is -2, I should have 2 real unequal roots. Or k is -3, or k is -5. But if I chose something like k is 0, I will not have 2 real unequal roots. Okay? We'll go on to another question now. Exercise 10.3, question 13. Find the exact values of p if px squared minus 2x plus 3p equals 0 is negative definite. Now, before we start the question, we need to look at what negative definite means. Now, I'll just do a quick sketch of what negative definite would mean. It would mean that the parabola would be below the x-axis at all times, and that for it to be below the x-axis at all times, it must be concave down, because if it was concave up, it would actually eventually cut through the x-axis. So this is negative definite. So negative definite, we can see that the discriminant is less than 0 because there's no real roots, and we can see that a, the coefficient of the x squared term, is also less than 0. Okay, so, but our a in this case is p. Okay, so p must be less than 0. Let's work with the discriminant first, and then we'll make sure that p, whatever we get for the values of p for that we get, that they are always less than 0 as well. So for negative definite, we know that the discriminant is less than 0 and that the p value there must be less than 0. So let's look at the discriminant being less than 0 first. So b squared minus 4ac has to be less than 0. Now in our question, a is p, b is -2, and c is 3p. So substituting those all into this equation here, I get b squared is -2 all squared, which is +4, minus 4 times p times 3p is less than 0. In other words, 4 minus 12p squared is less than 0. Now this is a quadratic equation because it's got a squared term in it. So you are not to take the 4 over to the other side or anything like that. You must factorize. So let's take out 4, seems to be a common factor here. So let's take that out. We're left with 1 minus 3p squared is less than 0. Now, this, in other words, if that's all less than 0, I can divide both sides by 4 and I'll get 1 minus 3p squared is less than 0. Now, this is almost looking like a difference of 2 squares. I do want to factorize this. So, what I can do, you can actually write any number as a square number because 3, if I look at 3, it's really root 3 squared. So I can write 3 as a squared number because it's root 3 squared. For example, 5 will be root 5 squared. 7 is root 7 squared. So I can write this as 1 squared minus root 3 times p squared is less than 0. In other words, making this left-hand side here a difference of 2 squares. Remember that a squared minus b squared is equal to a minus b, a plus b. So I've got 1 minus root 3p, bracket, 1 plus root 3p is less than 0. So now I've factorized this quadratic. Now factorizing the quadratic helps me sketch the parabola. I'll just move this down and I'll just focus it. Okay? So I want to sketch this parabola. If I just look, all of this is the same equation. If I want to sketch, actually it's all originally this parabola. All right, so I can see I've got a y-intercept of 4 and it's concave down. So the parabola does look like this. It's got a y-intercept of 4 and it's concave down. My roots, if I just solve and put this equal to 0, so I can see what the roots of my parabola are. So just first I want to solve this to find my x-intercepts of my parabola. I will get that p is 1 on root 3 and p is negative 1 on root 3. So if 4 is, this is the parabola I'm trying to sketch, okay? I know I've divided it by 4, but this was the original parabola. It's concave down because the p squared term is negative, and the roots are 1 on root 3 and negative 1 on root 3. So what I'm trying to do is I'm trying to see where is this parabola less than 0. Well, it's less than 0 underneath the x-axis. So therefore my solution is that p is less than negative 1 on 3 and p is greater than 1 on root 3 because it's these x values as well. But if I go back to my definition of negative definite, I know that for negative definite, my discriminant's less than 0, and I've done that and I've solved it and I've got these two solutions. But there is another thing, that I need to look at. For negative definite as well, I need to make sure, that p is less than 0. But here I've got this part of my solution tells me that p is greater than 1 over root 3, which means that this is positive. See, p has to be negative. P is less than 0 means that p's got to be negative, which means that solution is out. So, but p must be less than 0. Therefore, so this is just saying, but p is negative. So therefore, I can only take the negative answer here. So therefore, p is less than negative 1 on root 3. And that is my solution. Okay, sorry, it's just cutting out a bit. So there we go. P is less than negative 1 on root 3. Of this video are homework problems from the lesson on Thursday, the 15th. I think it's the 15th today, or the 6th, maybe it's the 16th, I don't know. But it's homework problems from exercise 10.3, okay? Now, the first question that was asked in class today in exercise 10.3 was question 8. And the question was to prove that 3x squared minus x plus 7 is greater than 0 for all real x. Now, if a graph is greater than 0 for all real x, what it's telling me is that, well, let's just look at the graph. For a start, it's concave up. So a equals 3, which is greater than 0, so it's concave up. And for this parabola to be always greater than 0, then it also must be positive definite. So in other words, the parabola always has positive y values. That's what greater than 0 here means. So the parabola always sits above the x-axis. Now, for it to sit above the x-axis like that, that means that the discriminant's less than 0 because it's got no real roots. And we can see that the that the value of the a, which is the coefficient of the x squared term, is positive, so it's concave up. So therefore, this question is really asking, prove that that parabola is positive definite. So we need to look at the question like that. So we need to interpret that as saying, prove that this parabola is positive definite. So remember, for positive definite, discriminant's less than 0 and a is greater than 0. We can already see that a is greater than 0 here. So we want that the discriminant is less than 0. So here is my discriminant. It's b squared minus 4ac. Calculating that out, we get negative 1 squared minus 4 times 3 times 7. We work that out and we get that the discriminant is negative 83, which is less than 0. Therefore, there are no real roots. So because there are no real roots, then we know that it does not cut the x-axis. But then we need to also make sure that a is greater than 0. So I can say, and we know that a equals 3. Actually, I've got it up there. And a equals 3, which is greater than 0. Therefore, my parabola is concave up, and therefore my parabola sits above the x-axis. And here I've sketched it. Actually, I did the question like this. Now, so what we can do, if I look at that parabola and I decide to try and solve it using the quadratic formula, when I work out the b squared minus 4ac bit, I'll get negative 83, and that's why this, I have no x-intercepts, okay? So that's why also why my parabola sits up here and does not cut the x-axis, okay? So that was question 8. And then what we did at the beginning of today's lesson, we just went over again all the different scenarios that you can get with the discriminant. So for 2 real roots, we know that the discriminant is positive. Now, if the discriminant is positive and the discriminant is a squared number, then the roots will also be rational. So if discriminant is greater than 0, we've got 2 real roots, but also if the discriminant is a squared number or a square number, then the roots are rational as well. Okay, now I think I discussed that in the last video. Our other scenario is that we've got 1 real root, or what's called 2 equal roots. In that case, the discriminant equals 0. Okay, you can have a concave up and a concave down situation there. And our third case is that you've got no real roots, and you've got no real roots like this, and this one's positive definite, and for that, discriminant's less than 0, but a is greater than 0, meaning it's concave up. And in this one, discriminant's less than 0, but a is less than 0 because it's concave down, and this situation here is negative definite. So we've got positive definite and negative definite are the 2 situations for no real roots. Quickly looked at the beginning of the lesson was, if you've got rational roots, you know how the discriminant's greater than 0, but if the discriminant is a square number such as 25, what will happen is when you do the square root of 25, you get 5. So you'll end up with roots that might look like this. This is just an example, all right? I just made it up. You could get negative 2 plus 5, which is 3 over 2, or say negative 2 minus 5, which is negative 7 on 2. Now these are 2 real roots, and they happen to be rational numbers because they can be written in the form of a over b, where b does not equal 0. So if you've got discriminant greater than 0 and a square number, such as 25 or 36 or 16 or 9 underneath the square root sign, then you can square root that square number to get a whole number, and therefore your 2 roots will either be whole numbers or fractions. And as they will be rational because they can be written in fraction form. Now, with equal roots, just going over that one again, where the discriminant equals 0, equal roots means that you've got 2 real roots. Here's an example of an equation that would give you equal roots and where the discriminant would equal 0 if I worked this out, okay? So if I looked at the discriminant of this equation, I would get 0. If I factorize this, I get x minus 3 squared equals 0. So because that's really x minus 3, bracket x minus 3, I've got 2 roots, and they are 3 and 3, but they're equal. Therefore, it's really the same as 1 real root, x is 3. And therefore this is a parabola that's just been shifted to the x equals 3 position. If I look at something like this in terms of roots, but this is not with this topic, X minus 1 cubed means I've got 3 real roots, but they're equal roots. I've got 3 equal real roots. In other words, I've just got the one, what I call triple root, okay, at x equals 1. This is called a double root, okay? We call it a double root when we do the polynomials topic, but in the quadratic topic, we call it 2 equal roots or just 1 root, okay? That's the end of this part 2 video, and exercise 10.3 part 3 video is the rest of the lesson from Thursday, and I think I've also set the homework at the end of that lesson. Thank you.